Parallel programming enhances computational efficiency by dividing tasks across multiple processors. It involves techniques like data parallelism and task parallelism. Understanding the programming interface is crucial, with message passing interface being a key tool. Message passing interface facilitates communication between processes, enabling scalable and efficient parallel computing solutions. Parallel programming involves multiple processes working simultaneously to solve complex problems efficiently. The programming interface is crucial for managing these processes. MPI, or Message Passing Interface, requires explicit communication management by the user, ensuring precise control over data exchange between processes. MPI is a multi-process model where users manage explicit communication between processes. In contrast, OpenMP is a multitasking model with implicit communication managed by the compiler. Understanding these differences is crucial for selecting the appropriate parallel programming interface for your computational needs. MPI, or Message Passing Interface, is a standardized library of subroutines available in Fortran, C, and C++. It enables coordination of programs across distributed memory environments and is flexible for shared memory use. MPI's scalability is not limited by processor count on a single node, making it ideal for diverse computing clusters. MPI is a standardized library of subroutines available in Fortran, C, and C++. It enables coordination of programs across multiple processes in distributed memory environments and is flexible for shared memory use. MPI supports scalability beyond single-node processor limits and can be compiled on various platforms and clusters, whether homogeneous or heterogeneous. The MPI environment begins with an initialization function, crucial for every MPI program. This function must be the first MPI call, enabling command line arguments to be passed to all processes. The environment concludes with a termination function, marking the final MPI call, ensuring orderly shutdown of the message passing library. The rank of an MPI process is obtained within a communicator, such as MPI COM world, initialized during init. This rank is crucial for identifying processes. Additionally, the total number of processes within a communicator can be retrieved, aiding in efficient resource management and task distribution. Communicators in message passing interface are crucial for managing process groups. Each process has a unique rank within a communicator, starting from 0. The default communicator, MPI COM world, includes all processes. Multiple communicators can coexist, allowing a process to belong to different groups, each with a unique rank, facilitating flexible communication setups. Point-to-point communication involves data exchange between two processes, forming the foundation of all message passing interface calls. In contrast, collective communication engages all processes within a communicator through a single call. It includes data movement like message passing interface, bcast, reduction operations such as message passing interface, reduce, and synchronization using message passing interface barrier. Point-to-point communication in message passing interface involves two processes exchanging data. The send operation is blocking, meaning it returns only when the buffer is free for reuse. Similarly, the receive operation is blocking, returning only when the data is available. This ensures a reliable two-way communication between processes. Blocking communications in MPI require the sending process to wait until data is fully transferred to the system buffer, and the receiving process waits until data is completely moved to the receive buffer. All collective communications in MPI are inherently blocking, ensuring data integrity by completing transfers before proceeding. Non-blocking communications in message passing interface return immediately after initiating data transfer, enabling overlap of computation and communication. However, caution is needed. Updating send and receive buffers before transfer completion can lead to incorrect results. In MPI, non-blocking send and receive operations, such as MPI iSend and MPI iRecv, enable point-to-point communication without halting program execution. To ensure completion, MPI wait and MPI test are employed. MPI wait is non-local, completing when the request is done, while MPI test is local, returning true if complete, false otherwise. Deadlock in message. Passing interface occurs when a process waits indefinitely for a message that never arrives, often due to blocking calls. This can necessitate aborting the program. Deadlocks may not always occur, as they depend on the size of the system buffer. Understanding these conditions is crucial for efficient parallel programming. In MPI's broadcast operation, a root process sends data to all other processes within the same communicator. This requires all processes to call the function with identical arguments. It's particularly useful for distributing input parameters read from a file, ensuring all processes have consistent data. In MPI's gather operation, a root process collects data from all other processes within the same communicator. Each process must call gather with identical arguments. Ensure the receiving buffer is adequately sized to accommodate incoming data. This operation is the inverse of scatter, where data is distributed from the root to other processes. In MPI's scatter operation, a root process distributes distinct data segments to each process within the communicator. This is the inverse of gather, where data is collected. Ensure each process receives the correct data portion, and the root process manages the data distribution efficiently. In MPI's reduce operation, a root process gathers data from all processes within a communicator and performs operations like MPI sum, MPI min, MPI max, and MPI prod. Logical operations such as AND, OR, and XOR are also available. Users can define custom operations using MPI op-create for tailored data processing needs. MPI all-reduce performs a reduction operation across all processes, ensuring each process receives the result. This is crucial for operations like summing values or finding maximums, where every process needs the final outcome. Unlike reduce, all-reduce distributes the result to all processes, enhancing data consistency and availability across the communicator. MPI barrier is a blocking operation used for process synchronization. It ensures all processes wait for each other, which can reduce parallelism. Use it sparingly, as it can be costly. It's essential when precise coordination among processes is required within a communicator. MPI init initializes the environment, while MPI com rank and MPI com size determine process rank and number. MPI finalize deactivates the environment, and MPI abort stops programs. MPI W time measures execution time. Point-to-point communications include MPI send, iSend, receive, iReceive, and send receive for message exchange, with MPI wait and wait all managing non-blocking operations. Collective communications involve bcast, scatter, gather, all-to-all, reduce, and all-reduce. Communicators in message passing interface allow partitioning with message passing interface COM split, creating Cartesian topologies using message passing interface cart create, and managing ranks and coordinates. Message passing interface input-output facilitates file operations, including opening, reading, writing, and closing files with explicit, individual, and shared pointers. Symbolic constants like message passing interface COMWorld and message passing interface success standardize operations across different environments. MPI, or message passing interface, is essential for parallel computing. It enables communication between processes in distributed systems. Key functions include MPI init to start, MPI com size to determine the number of processes, and MPI com rank to identify each process. MPI finalize concludes the program, ensuring all processes terminate correctly. In this message passing interface example, we initialize the environment and determine the number of processes and the rank of each process. Process 0 sends an integer to process 3 using MPI send, while process 3 receives it with MPI receive. The MPI barrier ensures synchronization before finalizing. This demonstrates basic point-to-point communication in message passing interface. This code demonstrates message passing interface point-to-point communication. Process 0 sends an integer to process 3 using MPI send, while process 3 receives it with MPI receive. MPI barrier ensures synchronization among processes. This example highlights the basic send and receive operations in message passing interface, crucial for parallel computing tasks. In this example, we compute P using numerical integration with the rectangle method. Each process calculates a segment of the loop, contributing to the sum. The MPI reduce function aggregates these partial results into a final value of P on the root process. This demonstrates efficient parallel computation, reducing execution time significantly. In this MPI example, a broadcast operation is demonstrated. The root process, identified by rank 3, sends a double value to all other processes. Each process prints its rank and the received value before and after the broadcast. This technique is essential for distributing input parameters efficiently across multiple processes. Compiling an MPI program is similar to compiling a regular C or C++ program. Use MPIC for C and MPIC++ for C++. For instance, to compile myprog.c, execute MPIC o2, myprog.c. This command optimizes the code and creates an executable named myprog. Thank you for your attention. We hope this presentation has provided valuable insights into compiling and running message passing interface programs effectively. Your engagement is appreciated.